Let's take a look at our transformation again more critically. First, we have the line that represents the motion of the back of our train. This line has a slope on the red axis, which is 1/4, and we have to take the square root of that number to get our contraction factor of 1/2. Let's now focus on the first event we considered. We choose it again because the way it moves is very simple. Its coordinates are t equal to 4 seconds and x equal to 4 light seconds. Now we perform the contraction to end up with t equal to 2 seconds and x equal to 2 light seconds. Remember that expansion along L does nothing this time. Well, that was quite a change, from t equal to 4 seconds to t equal to 2 seconds. Apparently, that event happened 2 seconds earlier for the person in the train than for the person in the railway. That is very counterintuitive. It should be just the same time, right? The key to unlock this mystery is the following. It might not be obvious, but our train is moving very fast. Let's take a look at our beloved event on the yellow line again. It has coordinates x equal to 1.5 light seconds and t equal to 2.5 seconds. In order to get the speed of the train, all we have to do is distance covered divided by time. That is 1.5 light seconds over 2.5 seconds, giving 0.6 light seconds per second. Remember that the speed of light is 1 light second per second in our units. Our train is moving at 60% of the speed of light. I am sure you have never moved that fast. We are allowed to expect strange things to happen there where we have never been. Here you have another one. In addition to the change in time, which is certainly unexpected, we see that the position coordinate of the event does not seem to transform correctly. During the 4 seconds before the event, the train moves a distance equal to the velocity of the train times those 4 seconds, that is 0.6 times 4 equal to 2.4 light seconds, approaching the location of the event. We should then have that the position coordinate of this event with respect to the train should be x minus vt. That is 4 light seconds minus 2.4 light seconds, which is equal to 1.6 light seconds. Our transformation does not give us that number. It says that the position of that event in the train will be x equal to 2 light seconds. Well, at least we must accept that it was not terribly wrong, and since the train was so fast, it might be even right. We have never tried, actually. Also note that for our event on the yellow line, everything is just fine. Since the event is sent to 0, which is obviously x minus vt, since the x value is vt itself. But wait a second. Our transformation is supposed to work for any train velocity. What happens if we choose a more standard speed for a train? Let me draw the yellow line for a speed of 360 kilometers per hour, which is 100 meters per second, or roughly 0.0000003 light seconds per second. Clearly a tiny number as compared to 1. A velocity of 0 would be represented by a vertical line. As time passes, we remain at x equal to 0. We just don't move. In our diagram, the line that represents the motion of the train is almost like that. Let's draw it. We cannot even tell that it is not perfectly vertical. We know, however, that it has a tiny slope in the xt axis since the velocity is not exactly 0. But remember that the slope we need is the one with respect to the red axis. A perfectly vertical line will have a slope of 1 there, and consequently the contraction factor derived from it would be 1 as well. That means doing nothing, of course, just keeping points where they are. If the slope is just a bit smaller than 1, we'll move points just slightly. Let's look at our initial point again. We start at x equal to 4 and t equal to 4 and move just a bit. I am greatly exaggerating here so that you can see something. The time of the event we are considering will be just very slightly different according to the train. This tiny fraction of a second is very hard to detect by a human and consequently we never notice it. For the position of the event, things are, however, quite different. Since we are talking here about a tiny fraction of a light second, which is a large distance of 300,000 kilometers, we might still get a change which is well within the human scale experience. The question is, of course, has the position of the event been reduced by the distance that the train traveled in 4 seconds, which is 400 meters? Remember that the train is getting closer to the location of the event during those 4 seconds until the event happens. If this is not the case, we are in trouble, since we know how things work for low velocities. That is directly accessible to our daily experience, and it has built up our intuitions about space and time. We'll take a look at this in our next video.